All right, so I see many people are connected on Zoom. We have also gathered a good number of people in presence, so I think we're ready to start. It's a pleasure to have Géraldine Servant open the last day of the symposium. It's nice to welcome her back. She was visiting GGI a couple of weeks ago, and she's going to talk about primordial gravitational waves boosted by axions. So thank you very much.
Good evening. Thank you very much to the organizers for setting up this 4-week event. I had a wonderful time at GGI 2 weeks ago. So in this talk, I would like to report on some work which was out in those 2 preprints together with my long-term collaborators, Pira Simakashon and Yann Goutenoir. So the aim is to show that early universe axion physics can naturally induce from non-trivial cosmological history, namely kination era, which is associated with some distinctive signatures in gravitational waves. And the main novel aspect here is that we go beyond the assumption of vanishing velocity of the axion. So before I move to this, our main general interest is to look at the impact of the cosmological history on gravitational waves and to go quite systematically over the, revisiting the predictions for the primordial gravitational wave backgrounds when taking into account a non-standard cosmological history. By non-standard, I mean non-radiation era. In fact, as you can see here on this plot, if you have a period where the energy density of the universe is dominated by matter, you will have actually a suppression of the gravitational wave signal compared to the standard prediction. And in contrast, if you have some kind of kination era where the total energy density of the universe redshift like 8⁻⁶, in comparison, gravitational waves which redshift as 8⁻⁴, they will get kind of enhanced. So you can get some very interesting signatures from this. So here are the 3 canonical examples of primordial gravitational waves. Primordial inflation, this is irreducible. This is at least the one which we are sure is there, coming from the amplification of initial quantum fluctuations of the gravitational field during inflation. You could also have cosmic strings, a network of cosmic strings. And finally, first order phase transition. So these are the 3 main backgrounds which have been extensively studied. And what we are interested in is to look now at the impact of non-standard cosmological era on these predictions. So here, these are the predictions assuming standard radiation era following inflation. Okay, and so here I'm stressing that we have a series of upcoming experiments which will range many frequencies from nanohertz to essentially kilohertz. And each of these frequencies can be associated to an energy scale of the universe. So by probing gravitational waves at different frequencies, we are essentially probing different energy scales in particle physics. I would like to stress this background from cosmic strings. It's particularly interesting because gravitational waves from cosmic strings, they really span a huge range of frequencies, and they are really a picture of the cosmological history. So here you see the prediction in blue. And so at a very high frequency, you have a cutoff, which comes from the formation of the network. But you could have actually cutoffs at lower frequency due to the fact that your loops, cosmic string loops, they will actually decay preferably into particles rather than gravitational waves. So you can actually probe the microscopic structure of your loops by studying if you are able to measure the spectrum at this very high frequency. At the moment, we have absolutely no experiments in this range, but I'm pointing out that in principle, you would, if you were able to probe this part of the spectrum, you would have access to some interesting physics. What I want to point out here is this nearly flat part of the spectrum, which is really a prediction following the assumption of radiation domination. And what we have been looking at is as soon as you drop this assumption of a long radiation era and you just have some temporary epoch where you deviate from radiation domination, you will have some very interesting features in this spectrum. And therefore, you would be able to essentially get some information about particle physics at very high energy scale by measuring these features in the spectrum. Okay, so now let me move to a kination era. So first of all, I want to discuss the case of this irreducible gravitational wave background from inflation. This is the most conservative approach. Even if there are no cosmic strings or no first order phase transition, at least we expect a background from inflation. And this background is predicted to be flat, as you see here, following the assumption of a radiation era following inflation. What happens as soon as you invoke some kind of non-standard cosmological evolution, your spectrum can be dramatically different. And in fact, if you have some kind of intermediate matter era followed by a kination era, which I will motivate later, this can lead to a very interesting peak. And now you see that you would be able to probe inflationary background with Einstein telescope or even LIGO here. So that's what I am very motivated by. I'm interested in the possibility that such era could happen and what can indeed lead to such cosmological evolution that would have really striking implications for gravitational wave backgrounds. So let's take the very simplest kination era. So what is kination? Is the universe is dominated by kinetic energy of a scalar field. Here is the equation of state, omega equal +1. So you could think of what happens at the end of inflation. Your field starts rolling and somehow you're dominated by kinetic energy. So this has been considered. In fact, kination after inflation is what you find in the literature. But it's actually very constrained because in fact, you would have such a huge signal in gravitational waves that it's essentially excluded. So let me show here what would happen if you had such a kination era following inflation. You would enhance dramatically your signal of gravitational waves, but we have these strong bounds from BBN and CMB on the number of extra relativistic degrees of freedom. Gravitational waves behave like radiation. And so if you have a long kination era following inflation, this is essentially excluded by these BBN bounds. So there is an incompatibility here. There is no way you could expect to have a signal from kination after inflation at LISA or LIGO because it's excluded by this bound here. Now you could try to see, okay, let's lower the scale of inflation, but when you lower the scale of inflation such that you would have a cutoff here, you also suppress the overall amplitude of your gravitational wave signal, which goes like the force power of inflation scale. So the lesson here is that there is no chance to see such amplification of the gravitational wave signal at the planned experiment. However, if we have some future experiments at very high frequencies, then you could probe such an era. And this is what we have illustrated here in this plot with very high frequency experiments. There is still an option to detect gravitational waves from very early kination era without violating the bounds from BBN. Okay, so now I want to move to something different. I want to move to a kination era which has nothing to do with inflation and which is going to motivate, which is motivated instead by axion physics. So the key point here is that you could have a kination era which is rather short, only a few e-folds inside the radiation era, so much after inflation, has nothing to do with inflation, inflationary sector. And this will still lead to very striking gravitational wave signatures. Okay, so the key question is what can trigger such kination era? And the answer is a spinning axion. Okay, so how can you get, what is the spinning axion? So the key point here is to go beyond the usual assumption. So, you know, most of the literature on axion cosmology assumes just consider the axion, which is at rest. At some point, the mass becomes larger than the expansion rate of the universe and the axion starts oscillating. However, one has to remember that the axion comes originally from a complex scalar field, and it has a partner, which is the radial mode. And the dynamic of the radial mode could actually induce a very different story. So you could, in fact, start at very large vacuum expectation value for the radial mode. When the mass of the radial mode becomes larger than the expansion rate of the universe, the radial mode starts to move, oscillate, and if there is some source of explicit breaking of the U1 symmetry, you will give a kick to the axion as well. So the axion will start rotating, and when it reaches the bottom of the potential, you can induce a kination era. So the energy density can be dominated by kinetic energy of the axion. So that's the background here. And in fact, these are the 4 requirements for such successful kination story. You start initially at rather large VEV, larger than FA. There is some source of explicit breaking, which is essentially active at early times, but becomes very suppressed later because it's suppressed by higher dimensional operators. And then you will need to damp the motion of the radial mode to make sure you can have kination. And so here is what would happen. You would have, so you have your standard inflation, standard reheating, you have your radiation era. And at some point, the energy density of the scalar field dominates. So, once your field has started to move, you will have oscillations, so you induce a matter era. And at some point, when you reach the bottom of the potential, you can get this kination era. So the energy scale of kination is controlled by your initial velocity here, your theta dot, and FA. And theta dot is actually controlled by the mass of the radial mode. So everything can be predicted by from your axion model, from your particle physics model. So you can express your kination energy scale, and you can actually also predict what will be the duration of kination as a function of the model parameters. Okay, so that's the key point here. And now let's see what happened. What are the implications on your gravitational wave signal? So what happens is that for a long-lasting gravitational wave source, you will have the gravitational wave energy density actually tracks the total energy density. So you get an enhancement and you get this peak structure here. Okay, so in standard radiation, your spectrum from inflation would be totally flat. And now you get this enhancement from the gravitational waves which have a frequency, which enters the horizon during this non-standard era. Okay, these are the modes which get amplified. So you can okay, so let me show you the main result here. So what you get are these peaks, and these are for 3 different types, so 3 benchmarks, which you can find here. So depending on your energy scale of kination and duration of kination, you will get a peak either in the LISA bound or in Einstein telescope bound. So this is completely model independent here, and you see my only parameters are energy scale of kination and duration of kination. Then those 2 parameters, I can predict them in a given model. Of course, now the key question is whether those signals from a spinning axion can actually, or can arise also when axion is dark matter. And so the answer is yes for generic ALP. Now, if you concentrate on the QCD axion, you will find, so this is a clear prediction for the QCD axion, your peak is outside of the range of observability of planned experiments. It would really be at the peak would be at very high frequencies. So this motivates this very high frequency gravitational wave experiments. Okay, I think I don't have so much time, so maybe I will skip. You can ask me later about the specific relation between the size of the gravitational wave signal and the relic abundance of axions. So let me just skip this and we can discuss later. I just told you the main point. For the QCD axion, your signal is really at high frequencies. But again, for generic ALP, you can have both axion dark matter and a large gravitational wave signal. Now, so far I discussed gravitational waves from inflation. Now you can do the same thing for gravitational waves coming from cosmic strings and study what will be now the deviations in the spectrum. So I remind you, this is what you get in standard cosmology, assuming standard radiation, rather flat background. And now in the presence of a short kination era, so again, we don't need a very long kination era, so it's just a few E-folds. You see here, they correspond to this benchmark, 2 E-folds, 4 E-folds, and 6 E-folds. So you get this beautiful enhancement from a few E-folds of kination era. And again, you can relate the peak frequency to energy scale of kination. And here, this is the scale of GMU, the string tension. Okay. You can do the same for global strings. So this was the prediction for local cosmic strings. And of course, the signal depends on the string tension. You can do the same for global strings, and this enhancement is particularly welcome because you know that the signal from global strings is typically smaller, but now with such an enhancement, it becomes accessible to LISA and even to LIGO. Okay, and let me continue now with, you have to put together the signal from strings and inflation. So in the previous slide, I was just isolating the signal from strings, but you have both inflation and strings. So when you put everything together, you will have this multiple peak spectrum here. So with one peak due to inflation, inflationary gravitational waves at LISA, and the peak coming from the amplification of the cosmic string signal at higher frequencies. Okay, and here is the same now for global strings, where you have this highly non-trivial structure, so very different from the spectrum you are used to from standard cosmology. Okay, so this is the prediction for gravitational wave background coming from a network, global cosmic strings, and primordial inflation. Okay, so I think I'm very much on time. This is a summary. Kination is a period when energy density of the universe is dominated by a scalar field with large kinetic energy. This amplifies primordial, long-lasting sources of gravitational waves. And this is actually well motivated when you consider axion models and the interplay dynamics between the radial and angular mode of a complex scalar field. This can very naturally induce such short, low-scale kination era. You can relate the position of the peak to the kination energy scale, and you see that for LISA, Einstein telescope, you can probe different types of energy scales. The peak frequency is also related to the duration of kination, and this result applies to any ALP, in particular QCD axion, dark matter, but in this case, the signal will be at very high frequencies. And I stop here. So, thank you.
Thank you very much, Géraldine, for the very nice talk. Are there any questions from inside the room? Well, I wanted to hear more about the QCD axion story that you skipped. So is there like a fixed frequency range for where you expect gravity waves in that case, or more like a broad area?
Okay, so let me go back to this. So you can relate essentially, so the Petershian charge in the spinning axion transfers to the axion number density. And so now the way you compute the relic abundance is via kinetic misalignment or so-called axion fragmentation. So it's, it's not the usual formula from standard misalignment. So there is a clear relation here. So you can essentially, the gravitational wave signal is is determined by this theta dot, which also determines the relic abundance. And you can relate the peak frequency to FA, MA, and your kination energy scale. So there is a clear prediction here. And now if you want to demand the correct abundance of dark matter, you have to be on this line. Going to the LISA or ET observability range would correspond to overclosing the universe with QCD axion. I don't know if
what
this
frequent is this line then peaking at some higher frequency?
So this line is the position of the peak of the signal of the gravitational wave signal from the spinning QCD axion. And when I move along this line, I essentially play with I see the let me see.
Okay.
I mean it's all given here. And now when you plug in, the relation between MA and FA that you have for the QCD axion, you are very constrained.
I see. Thank you very much. Yeah, I had missed the fact that was the peak. Now I see it on the y-axis, but during the talk, I had missed that point. Yeah. Thank you very much.
Let me stress that the signal from gravitational waves does not depend at all on the axion mass. So it's completely independent. It's really controlled by the initial velocity, which is controlled by the radial mode mass. So the axion mass only comes in when you want to have the correct relic abundance.
Yeah, so I have a very basic question. So it's about this kination phase, if just because I'm not familiar with it, just to make sure I understand it. So this kination phase takes place normally after inflation, and it just changes the background evolution. And so it doesn't really matter what happens to the inflation. This is a way for us to essentially spice up even boring inflationary scenarios, because as a result of this different background evolution, I get to have a blue spectrum, even starting from boring inflationary scenarios. Is that correct?
Yeah. So exactly. So until now, all the literature about kination was really tied to inflationary models, in fact. So what we were interested in is to see whether one can motivate kination completely independently of inflation. So you can have your boring inflation, as you say, whatever model of inflation you like. And then this kination has nothing to do with the inflationary sector. It comes from an axiom which has nothing to do with inflation.
All right.
The one I'm describing. Does this answer the question?
Yeah, you have to say it.
Yes, thanks.
Hi, I have a question about this initial velocity. Could you comment a bit more how this motion is transferred from the radial mode to the angular, the spinning axion?
Yes, okay. So here the 4 ingredients are summarized. So a crucial aspect is that you need some source of explicit breaking, otherwise you will not transfer any, you will not give a kick to the axion. So this is a very first important ingredient. So as soon as the radial mode starts to move, so when the radial mode becomes larger than the expansion rate of the universe, the radial mode starts to move and immediately it will give a kick to the axion. Okay. Now, what is very important is that later you damp also the motion of the radial mode, because otherwise you will remain in a matter era. So it's a very important aspect here of the dynamics, and maybe the most complicated one. You need to make sure that interactions in the plasma will in fact damp this, so the radial mode will essentially decay. So this is what we have studied in detail, and you can show in fact that there is a region of parameter space where this happens, but it's an important aspect. So
for the U1 breaking, probably you mentioned, is it achieved with higher dimensional operators or? Yes, so okay, and of course the other ingredient which is very important is this number 2, large initial VEV,
And so here's a way you can motivate this is by some negative Hubble-induced mass term. So this is quite well motivated. You have some negative, so minus h squared term in phi squared in your potential, which will drive your field. Yeah, you need to drive your field to values larger than FA. But this is well motivated in SUSY models, for instance. You can get this, and this was already done. I mean, this is not new. Already in all these papers, Randall, Dine, Thomas, where they clearly show how to do this, and this was exploited later in this paper by Ko, Hall, Harigaya. All these axiogenesis paper and kinetic misalignment papers, they exploit exactly this fact. So the crucial part is, in fact, you start at very large initial wave. So it's true, most of the literature, in axion cosmology, you assume the standard story where you are here, then you have a thermal phase transition, you roll here, and just you forget about your radial mode. But it's not necessary. I mean, you could have a very different story starting at large initial values instead. And this is how you would get naturally this kick for the axion.
Okay, I see. Thank you.
So I see a raised hand. Chiara, please mute yourself and go ahead.
Thank you, Géraldine, for this great talk. Of course, as a pulsar timing array person, I have to defend the honor of my experiment and look at one of your slides where you had cosmic string tensions, and I believe you had a tension of about G mu of 10 to the minus 11.
Okay, let me find it.
Yeah.
Yeah.
Here we are. Yes. So I wasn't sure whether or not you were aware of the fact that in the 2018 paper, we managed to set a limit on the cosmic string tension of about 3 times 10 to the minus 11 and omega GW of about 10 to the minus 10.
Yes. So here I'm taking essentially that's why I don't take any larger values for G mu. So I'm taking the value which is essentially, I think, still a load and show the prediction. Yes.
Right, because I was just a little bit difficult to see. I mean, obviously, as someone who works in this, if you have your line going right through my experiment, I'm very interested.
Okay, yeah. No, so of course, there is, as you know, there is a whole literature trying to fit the data with cosmic strings. And that's something, of course, which is very tempting. In fact, in the paper by, because what I'm discussing here was also discussed in a recent paper by Harigaya et al., where they also tried to motivate, to explain the signal with coming from a kination era, but this would mean the kination era has to happen after BBN, which is extremely constrained. So you could also play with trying to see whether you can have a very low scale kination era. That's what they tried to do in this paper. But yes, thank you. I'm aware of the constraints, and that's why I'm taking this value here.
Okay, wonderful. Thank you so much.
Any more questions, either here or on Zoom? Okay, so I mean, if online is anyone else has a questions, just unmute yourselves. All right, if not, we can thank Géraldine